Okay, guys, what we want to talk about here is several key properties that are going to be used throughout pretty much the rest of the course. So it's going to be pretty important that we pick up on these. Some of them are going to be review, some of them are going to be new to you. Pick up on them, know when to use them, and why we can use them, because they're going to be beneficial components to the proofs that we do within the next couple days, and then ultimately within the rest of the quarter and then the semester and then ultimately the year. First one, well, before we talk about anything, all of these are defined for arbitrary values. Okay, so any real number, any number that you can think of off the number line, this is going to work for. Okay, and it becomes very useful. A lot of times when we do this type of stuff, we won't really know what the numbers are. Okay, there'll be again arbitrary values, but these properties exist and they can be proven to exist regardless of what A, B, and C are. Now there's going to be a couple times where we have a requirement on maybe C. Come down here, C has to have that requirement that it can't be 0. But for the most part, regardless of the numbers, we should have properties existing all the time. Okay. First one, pretty straightforward addition property. You've dealt with this since you've started first solving equations, guys. If I have something like 2x minus 3 equals 9, okay, all of us know that the first step in solving for x would be to add 3 here and to add 3 there. And that's the way we see it. It's the way we deal with it, okay. Most people are going to feel comfortable using that opposite operation by stacking the numbers like this. But really what we're doing, if I have 2x minus 3 is equal to 9, really what we're doing is we're saying we're going to add 3 here, we're going to add 3 here, okay? And that's what's going on here, okay? It says if A equals B, okay? If A equals B, so our A and our B in that situation would have been that expression being A and that one being B. At the beginning, we just write what we had at the beginning, 2x minus 3 is equal to 9, that's what we started with. If this side here is A and this side is B, well, we know that we can add whatever we want to, in this case 3, but ultimately some third value, we can add it to both sides, as long as we do it to both sides. And that's the addition property of equality. Okay. Now the way we're going to see it and probably use it for the most part in geometry is it's going to look like this. We're going to have, let's say just a segment here. So we have A there, B there, maybe C, and then D. And I want to make the argument that AB, we'll start off with AB, is equal to CD. AB is equal to CD. So we've got in our picture here, let's just highlight it, we've got that distance being the same as that one. Okay. Well, now I want to make the argument, and you'll see why later on, why this would be important, but now I want to say that AB, do it black, AB plus now BC. Okay. So notice I started with the left side AB, and now I added something to that left hand side. Is equal to CD. Well, if I start with AB is equal to CD, and now I've added BC to the left-hand side, if I want to maintain this equality, I better add BC to the right-hand side. Okay. Now what we've done here visually is we started with this yellow segment AB, and now we've attached to it that segment right there, BC. So we're saying AB plus BC. And then we started on the right-hand side with CD, but we've added this black segment BC to it. So we've developed that. Okay. Well, what we should know then is if I start with AB, the yellow segment, add the black to it, and on the right-hand side I start with the yellow segment and I add the black BC to it, those two results, when I'm done, should still be the same. I've added the same amount to both sides, regardless of what BC was. Okay. Maybe if we start over with A being there, B, C, and D again, if we put measurements in here, okay, just put some concrete values in. Let's say this is 10, and that's 10, and let's say BC is 8. Well, we all know that 10 is obviously equal to 10. But now if I go 10 plus my 8, okay, so AB plus BC, well, that should still be equal to 10, which is CD now, plus the 8 that we gained from BC. Oh, 8. We should get 18 equals 18, right? And that's because we started with two things that were equal, 10 and 10, and added the same thing to both sides. But most of the time, like I said, we're not going to know those 10s and the 8, okay? We're just going to arbitrarily call them AB, BC, and CD. So that's the addition property of equality, something we've dealt with for a while now, and it's going to be very useful to recognize in this segment addition kind of concept. Subtraction property equality is the same concept, okay? Subtraction property equality now says if I start with something like, let's just use some different letters here. Let's say I start with X, Y, Z, let's put W down here. If I start with XY plus YZ is equal to YZ plus ZW, the subtraction property of equality says if you have the same thing on both sides, YZ and YZ, well, let's just get rid of them through subtraction, and you'd be left with XY is equal to ZW, which would be nice information to know. So visually think about what we started with. We started with that segment there. Let me highlight instead. We started with that segment there being congruent to that length there. Okay? Well, if we wipe away YZ from both, okay, what that's telling us, what it leaves us with, is this smaller yellow segment and this smaller green segment, but they are now equal because we wiped away the same thing from both sides. So that's a subtraction property of equality. Notice that we're talking about equality here. Okay, it's very important that we recognize equal signs, and you'll see why in the next set of properties. Multiplication property of equality just says if I start off with two things that are equal, okay, if I start off with 3 is equal to 3, and I multiply both sides by 5, then I better get a statement that is still equal. 15 equals 15. Most of the time you would have seen this so far as a multiplication property of equality. Maybe we have like 1/2 x is equal to 5. We're saying those two things are equal. This is representing a number. This is a number. We can multiply this side here by 2, some c value. Multiply this side by the same 2, some c value. Okay, as long as that c is ascending on both sides, you would get x equals 10. So that's a multiplication property of equality. Multiply both sides by the same thing, and you're fine. Division property of equality, same concept. You know, a lot of times you've probably seen it as if 2x is equal to 8, you would divide this side by 2, divide that by side by 2, and you get x to be 4. Okay. Well, the 2 that you chose from both sides is some arbitrary constant c. Okay. Now we have some algebraic properties and rules that tell us what to choose here. But I could have done anything. Could divide it by 3. Could divide it by 100 if I wanted to. As long as I do it to both sides, I'm allowed to do division. Okay. The only thing we got to be careful of is that you can never divide by 0. It's one of the main kind of pillars in mathematics and in our arithmetic that you cannot divide by 0. The reflexive property, this one is very useful. You do it all the time. You might not recognize it. For instance, if I write this 2x minus 3 is equal to 10, go back to that. Or I guess we had 9 earlier. Go back to that. Okay. A lot of people will put plus 3 and then plus 3. But what we're saying here in that notation is what I'm going to do, I'm going to add the same thing to both sides. The additive property of equality, addition property of equality allows that to happen. But what we're telling everybody is that what I'm adding to the left is, that's what that means, is exactly the same as what I'm adding to the right. Okay? And that's what we're coming up with here. Okay? The reflexive property says something is always equal to itself. Okay? 10 is equal to 10. R is equal to R. Okay? Doesn't matter. As long as you see the left-hand side is identical to the right-hand side. That's the reflexive property. Symmetric property. Okay, what I think about symmetry is kind of folding. Okay, using lines of symmetry. So if I were to fold on that line right there, you see that that B and that B would land on top of one another, and this A and that A would land on top of each other. Symmetric property of equality. What it's all about is, you guys have done this before. If I have like 3 is equal to 1/2 x plus 7. Some people don't like seeing it that way, so they rewrite it then. So this is kind of what we start with. If we start with this, then we can rewrite it as 1/2 x plus 7 equals 3. It just allows you to flip the left-hand side and the right-hand side. For your convenience, it might make things seem a little bit easier for some of us. But what allows that to happen is a symmetric property. Transitive property, this one is probably going to be used quite a bit, or I know it will be used quite a bit. And it is if A is equal to B and B is equal to C, then A is equal to C. Okay, so we've got multiple things going on here, and it's a linking process. It's a linking property that links 2, 3, 4 different things together through equality, and then ultimately you can choose any 2 of those that you want to say that they're equal. So, for instance, if I say, usually it's the way we'd say it or see it, we say like segment AB's length is the same thing as segment BC's length. But BC's length is the same thing as CD's length. And CD's length is 4. So we might be able to see this and say, okay, AB is the same as BC, but BC is the same thing as CD. But CD is the same thing as 4. So it allows us, in its purest form for the transitive property, says that AB is now 4. Because we're able to link AB to BC, BC to CD, and CD to 4. But really what can happen is I can say anything. BC is 4. Okay, because that BC goes to CD and CD is 4. Okay, so the link can be, I've got 1, 2, 3, 4 different things here. Okay, AB, BC, CD, and 4. And if they're all equal to one another through this linking process, I can pick any 2 of them out and state that any 2 of them are directly equal. It might be easier to talk about. Okay, we kind of talked about the transitive property a little bit with our linguistics and the law of syllogism, okay, and how we link a conclusion to a hypothesis, and that then allows us to make the first hypothesis pair up with the last conclusion. The last one, substitution property, again, a very useful tool. We use this all the time. You guys did this all the time last year. Say we have like y equals 2x plus 8, and you guys said, okay, I'm going to start plotting some points. So we let our x value and our y value go there, and you just start choosing 0, 1, 2 for your x's, and now you plug those in. Okay, so when I plug something in, the math term I'm using is substitute. Okay, so I would substitute the x with a 0, and I would get 8. I would then substitute the x with a 1, and my y would be 10, and then I'd substitute the x with 2, and my y would be 12. Okay, so those are some things, some substitution things that you've seen. What we're going to see geometrically is, we might say that measure of angle ABC is equal to the measure of angle 2, and then for some reason, maybe down the road, we would say measure of angle 1 plus measure of angle ABC is equal to 180. Maybe we come up with that rule later on. Maybe we use the picture that we are provided shows 2 angles being added together, and we see that they're maybe a linear pair or something like that. Okay, or that we're just told that they're supplementary. But now what might be useful is say, well, I know from prior that ABC and 2 were equal. So what I could then develop is a new statement that says measure of angle 1, and now instead of ABC, replace it with what it's equal to, measure of angle 2. Now those 2 things add up to 180, which is a whole new statement than what that was, because attached to these things will be pictures, and angle 1 and angle 2 and ABC will be all over the place. And this would be new information garnered from knowing these two facts. So it's pretty useful. Substitution property is it's a very, very, very common property. As we start proving things, I tell people, you get stuck, think substitution. That might be a property that we use maybe 60% of the time. It's very, very prevalent. So those are properties of equality. This is distributive property. This is just something that I want to make sure we all understand. Distributive property just means to give. If I were to distribute information, that's what I'm trying to do with this video. I'm trying to give you all this information. Like a paper boy will distribute the newspaper to the residents and stuff like that. So distribute means to give out or to pass out. So that's what we're going to do here. We're going to give this value here to everything inside the parentheses. Okay, and you see that being done with the arrows. You guys understand distributive property, so just kind of reiterating what we know from the past. But if I've got something like this, so maybe I've got 2 and then x plus 3 on the inside, well, that becomes 2x plus 6 once I distribute that and then distribute that. Okay. Same thing can happen with a difference. It doesn't matter whether this sign's positive or negative. What people forget to realize, though, is something like this. We talk about combining like terms. You hear that phrase all the time. Like if I have 2x plus 5x. Hopefully we all know we can reevaluate that, simplify it to 7x. But a lot of people don't know why we do it. We were told that in maybe Algebra 1, but why? Okay, and here's the logic. If I have 2x plus 5x, I'm going to actually think about working my way backwards. Okay, so let's say that was this phrase right here after we've already done distributing. Okay, well, if that's what after I've done the distributing, we're going to recognize that there should be some factor that was common in both those. And we see in 2x and the 5x, there is a factor that's common. The factor would have been x. So maybe I could have started with something like that. Hopefully that makes sense. Okay, if I factor that x through, or it's not factor, distribute that x through, I get 2x, which is that, plus 5x, which is that. Okay, but now with order of operations, we know we can do that 2 plus 5. Well, that gives me 7, right? So I got now x and a 7. We'll multiply those together. We write the coefficient first, and we get 7x. Okay, so when we see people say, well, combining like terms, you're using distributive property. That's why we can combine like terms. Okay, and you're going to see that in Math Excel when they say, they'll have something like maybe 2x plus 3 plus 4x, and they want to rewrite that as 6x plus 3, but then you're told to choose from like a drop-down window. What was that property that allowed you to do that? Obviously, we combine those, but there won't be in this drop-down window. There won't be a phrase combining like terms. The phrase will be distributive property of equality. Okay. The last group is really the same thing we've already talked about with equality, but now if you notice, all the things we're talking about over here are now congruence symbols. So remember, congruency is talking about the shape. Okay, so we have the reflexive property. Okay, which says basically, you start with a segment, it is always going to be 100% of the time congruent to itself. You can take that segment, cut it out, lay it back on top of itself, and they're congruent. Take an angle, any angle I give you, it will always be congruent to itself. That's the reflexive property. Symmetric property, just to, if I want to say that AB is congruent to CD, but maybe it's more convenient to talk about them in a different order. Okay, so let's say that's AB there, and let's say that this segment here is CD. Okay, if I want to say they're congruent, by all means, I can say AB congruent to CD, but I could have started with CD and said it is congruent to AB. You might initially think, well, that's kind of trivial, doesn't make a whole lot of sense to have that, but it's just telling you, ultimately, when you look at a congruency statement, they are two-way streets. You can start and read from left to right or right to left. Okay, and then we got the transitive property. The transitive property just says if I've got, let's say, just deal with segments. Okay, so I go back to A, B, C, D, and now I'll bring in E, F. If I've got these three segments that are congruent, the arguments are stated that AB is congruent, that segment is congruent to CD, okay, and CD is congruent to EF. Maybe that's all we're provided with, okay. We go through our problem, that's what we're provided with, that's what we're going to determine. But if that's true, we can see that this is kind of the middleman. CD is the middleman, and that's the link that gets me from AB all the way to EF. So now I can make the argument that AB is congruent to EF. And what happens is that this is a new argument. We know it's true, okay, and it wasn't initially provided for us. So this whole process is a tool. These properties are tools for us to develop new ideas, new thoughts, new true statements that were not provided. Okay, these properties are as important, if not more important, than some of the vocabulary that we deal with. Remember, we talked about, we're going to have a hard time with this course if we don't know our vocabulary words. We can't read the book that uses these terms. It's going to be a very difficult course. These properties they have to be something that you guys start learning, start using on a consistent basis. And on top of that, the associative property, the commutative property, and know, the associative property works for addition, works for a multiplication. The commutative property works for addition and multiplication, but the commutative property doesn't work for subtraction and division. Okay, so those things from Algebra 1 are going to be very important as well. Okay, going to have maybe a short quiz on Tuesday over this video just to make sure that we've all watched it. So please be prepared for that. Maybe 3-4 minutes. Okay, 1, 2, 3 questions, and then we'll go on. And the tool of this, the reason of this, was so we can spend more time on the nuts and bolts of 2.5 and do some of the proofs in class and be able to answer some of the questions you might have as we do those initial proofs.